What's the first image which pops up in your head when you think of an old detective film? Well, for most of us, the detective always appears in a dimly lit room. He carefully looks around, demystifies clues, and analyzes documents through his magnifying glass. A magnifying glass seems just like a piece of glass attached to a handle. But how does a magnifying glass actually work? Hello and welcome. I am Shaleen and today we will discuss refraction through spherical lenses. Did you know that the world's very first fictional private detective was Sherlock Holmes? Today his beloved deerstalker cap and magnifying glass have become iconic with his name. Yes, magnifying glass, the simplest example of a convex lens. In today's episode, we will focus sharply on the following. Number 1. Rules of ray diagram for image formation by spherical lenses. Number 2. Image formation by the convex lens for various positions of the object. Number 3. Image formation by the concave lens for various positions of the object. And also the exam decoded section. Now when we look through spherical lenses, we realize that what we see through it is dependent on where the object is placed. Consider a magnifying glass itself. Image changes as you move further away from the object. Now what is the scientific reason of this change? Let's find out. To make things simpler, there are certain basic rules we follow using which we can schematically represent the actual refraction process on paper. Keep in mind that laws of refraction are followed at all points of interface, whether the ray enters glass or leaves glass. To locate the image of an object, there are 3 rules that can be listed and followed. Of these, any 2 rules which are appropriate can be applied to locate the image for a given position. Rule number 1. A ray of light from the object that is parallel to the principal axis after refraction through a lens passes through the principal focus on the other side of the convex lens. However, note that in case of concave lenses, the ray appears to diverge from the principal focus which lies on the same side as the incident ray. Rule 2. A ray of light passing through a focus or appearing to meet at the focus after refraction will emerge parallel to the principal axis. Note that in case of concave lenses, the incident ray appears to pass through the principal focus if extended. Rule 3. A ray of light passing through the optical center of a lens will emerge without any deviation. This holds true for any ray incident at any angle with respect to the principal axis. As you can see, the principal axis itself is a straight line that passes through the optical center of the lens. Now, knowing the above rules, how do you think we can locate the image of an object? The position of the image of an object is the location where at least 2 light rays originating from the object intersect upon refraction through the lens. This would be clearer when we draw some ray diagrams. Now, what are ray diagrams? Ray diagrams are the schematic representation of the actual paths followed by the rays through one or more media. They enable us to identify the location of an image produced by a lens on paper. Remember the rules. We need to construct at least two sets of incident and refracted rays to locate the image of an object due to refraction. Let's consider now different possible positions of the object. Case 1. When the object is placed very far from the lens, we may presume it's at infinity. Its image is formed at the principal focus of the convex lens. Here, all the rays originating from the object are parallel, and hence, after refraction through the lens, converge at the focus on the other side. The real and inverted image formed at the principal focus is much smaller in size than the object. In fact, it is of a point size. Now let's get to the case 2. When the object is placed beyond twice the focal length of the lens, that is 2f1, the image is formed between f2 and 2f2 on the opposite side of the lens. The image formed in this case is real, inverted, and smaller than the object. Now let's take case 3. When the object is placed exactly at twice the focal length, that is 2f of the lens, then its real and inverted image is formed at twice the focal length, that is 2f2 on the other side of the lens. The image is of the same size as the object. Case 4. Let's move the object a little closer to the lens. When the object is placed between f1 and 2f1, then the real and inverted image of object is formed beyond 2f2. Now you will notice that the size of the image is larger than the object. Case 5. Can image be formed at infinity? Yes, why not? If the object is at infinity, the image was formed at the focus. What if we interchange the positions? When the object is held at focus, then in the case of a convex lens, its image is formed at infinity. The image is real, inverted, and highly enlarged or magnified. Did you realize, so far, as we move the object closer towards the convex lens, the image formed was always real, it was getting bigger, and the image was moving away from the lens. Now, what if I insist on moving the object even closer to the lens? This is case 6. If the object is placed in between the focus f1 and the optical center O of the lens. Drawing the ray diagram, we realize that the diffracted rays are divergent. Now the image can only be formed when the rays intersect. For this, we would have to extend the ray path backwards. The point where these virtual ray paths intersect is where the image will be formed. In our case, the image formed by the lens is on the same side as the object, beyond f1. The image is virtual, erect, and enlarged. This means that you can no longer receive the image on a screen. I'm sure that after that preliminary investigation, even the strongest detective would need a break. But while all you investigators out there cool your heels, do ponder upon this question, posted by one of you on our website, topperlearning.com. Does a ray of light passing through the focus of a convex lens emerge parallel to the principal axis after refraction? We'll find out after a short break. I'll be back in a jiffy. Stay tuned.